All right, welcome back, everybody. Now we're moving into our next section, which has to do with IP addressing and network address translation. We'll talk specifically about the different types of NAT that exist and how we implement NAT within our Cisco iOS environment. And what are the three different types of NAT that we can implement? We can do static NAT, we can do dynamic NAT, and we can do what we call port address translation, which is overload. Oftentimes we simply refer to that type of NAT as overload. Now keep in mind that this NAT that we're going to be talking about here is going to be related to Cisco iOS, not necessarily an ASA firewall or some other device that might be doing NAT at the perimeter, but the general concepts are still going to be the same with regard to the terms that we use to describe, inside local and inside global and outside local, outside global, and in general how NAT works as a protocol or as a process. So we understand generally the need for NAT, right? NAT wasn't originally designed to be part of IP. It was something that came along after the fact when they realized that there just simply wasn't going to be enough address space for all the clients to be able to communicate globally and have some sort of public IP address. So there were a couple of things that changed in the process of IPv4 that really made some significant changes and allowed us to really kind of preserve this address space that we have. One was classless interdomain routing, and the other one was private addressing and NAT, RFC 1918, and so on. So when we're doing that, of course, we're taking packet header information and we're translating it. Typically, it's going to be the source address, 10.1.1.100 in this case, which is a private address, might be translated to 209.165.205.5. We have some sort of perimeter device, whether it is a firewall or a router, and that perimeter device is going to be configured with a NAT policy. We might use an access list, for example, to identify who gets NATed, and then we're going to have a NAT policy to identify how NAT is going to take place. It could be a static NAT translation where we're just simply doing a one-to-one bidirectional NAT, which is permanent and always active in the database. Or it could be a dynamic NAT. Very rare. We don't typically see dynamic NAT too much these days, but dynamic NAT is where you're translating to a pool of addresses. And the other option would be to do what is the most common form of NAT, which is the overload NAT, where you're taking multiple inside local hosts and you're translating them to a single inside global address, and you're simply overloading that address multiple times, and keeping track of how those translations are taking place. We understand the benefit of NAT. The side effect of NAT is potentially security, particularly with dynamic NAT scenarios, because clients on the inside cannot be communicated to directly unless there's an active translation profile already in place. But the obvious benefit of NAT is that we're going to be conserving address space, and we only need a small group of public IP addresses to communicate to the internet. And that's like networking 101. It's certainly not something you guys aren't aware of. There are some downsides to NAT, though, as well. In a lot of cases, NAT will break the end-to-end concept of IP. IP was originally designed to be an end-to-end protocol, meaning that it was host-to-host, and having multiple NAT boundaries or NAT boundaries in between can kind of mess with that type of communication. Using NAT complicates things like tunneling, IPsec, those types of protocols, services that require things like TCP connections, from the outside. If they're running private addressing, that's not natively available because we can't initiate that connection to that particular device. So in those cases, we would have to use a static NAT scenario, and static NAT doesn't allow us to conserve address space. Static NAT is basically just a one-to-one translation. Also, NAT takes time, takes processing time. It takes time to translate and then untranslate these packets. We also have to have specific resources, memory resources, and CPU resources that are dedicated to these translations. We have a NAT translation table or database. And if you have thousands and thousands of connections, which is highly possible, even if you may only have hundreds of users, it's very possible to have thousands of connections because each client is generating multiple streams or multiple data flows. All right. So, you know, I mean, it's not like NAT is a new thing, right? It's been around forever. Everybody does it. Everybody uses it. So regardless of the benefits and regardless of the disadvantages, in most IPv4 environments, it's just simply required. It's something that we have to do. All right. So what are the benefits of using NAT? NAT uses few external addresses to support many internal hosts. That's a possibility, right? Certainly with overload, that's a possibility, and that would definitely be a benefit. NAT does not decrease switching delays, it increases them. It also does not enhance tunneling protocol use, it makes it more complicated. It also makes troubleshooting more difficult, but it does make it easier to change ISPs because you're not having to readdress your entire internal organization when you want to switch ISPs and maybe even change your public presence. You just simply have to change the NAT policies on the perimeter device, and that's what allows you to communicate effectively. All right. So this is, again, kind of like networking 101, not really difficult to understand. It's pretty basic stuff, right? And that in general has always been pretty basic. But let's still take a look at it and kind of get through this section here and move on to the next section. What are some of the NAT addressing types? Now this is one of the things that some people do get confused about. So I think it's an important concept to understand, is that we have a very specific way of defining the NAT addresses and what they mean in our topology. So inside simply means typically the source. It doesn't always have to be the source, but inside means where the traffic is coming from, your organization, in other words, and outside is usually the destination. Where is the traffic going to? Local means private, and global means public. So if I say, what is your inside global address? What is your inside global address? That means to say, what is the translated IP of your inside host? If I say, what is your inside local address? I mean to say, what is the real IP of your inside host? On the outside, what is the outside global address? Is what is the translated IP of the outside or destination host, and outside local would be what is the real IP of the outside host. Now, in most cases, we don't really differentiate between outside local and outside global because that information is hidden. We don't see that information necessarily in our communication channel. It's probably kind of hidden. But we could do natting of both source and destination. Sometimes we have policies that are required to do that, but generally the outside address for local and global is just going to be the public IP that you're aware of. So you'll see that often documented in NAT scenarios and NAT configuration examples where the outside global and outside local addresses are the same. So inside local, again, identifies the real IP of the client. Typically, that's an RFC 1918 address or a private address. Inside global is the translated IP. Outside global is the translated IP of the destination. And outside local is the real IP of the destination. All right? And this is not correct. This says, in most cases, the inside global and outside global addresses are the same. That is not true. Outside local and outside global is what they meant to say. Right? Inside global definitely isn't the same as outside global. That would mean that you're talking to yourself because your translated IP would go to their translated IP, but they would be the same. So that's just a typo. They meant to say outside local and outside global addresses are the same. And that indicates the destination address of that outbound traffic. A good way to remember what is local and what is global is to add the word visible. To me, I say local is private and global is public, right? But yeah, I can see it everywhere is what they're saying here. That means global. I can only see it locally. That means private. So local means private and global means public. All right. Let's see. If a host's address was translated, which of the host's address would an internet server see as the source of the packet? And that would be the inside global address. Again, a lot of people kind of infer that inside means somehow private, and that is absolutely not the case. Local means private, global means public. Okay? So when it comes to implementing NAT, we do have 3 different choices of implementing NAT. 2 of these are used quite often. 1 is not used as often. There is a special use case scenario for it, but it's typically in very large environments. So a static NAT is, which kind of defeats the purpose of NAT, is a one-to-one translation. For every inside local address, I have a single inside global address. The reason why static NAT is used is to allow bidirectional permanent communication. So I may have a server on my DMZ, or I may have a host on the inside of my network that the client needs to be able to communicate to on the internet, and that device needs to have some sort of publicly reachable address. All right, so the way that we do that is we do a static translation. We give that client a single NAT translation entry. The thing about static NATs, though, that make them really useful is that they are bidirectional. Other NATs, like dynamic NAT and overload, port address translation, require the session to be established from the inside out before any traffic can flow in the opposite direction. Static NAT traffic can flow in both directions automatically. All right. So that's the last one, port address translation. We call that a many-to-one translation scenario because we're taking, hundreds of hosts potentially or thousands of hosts potentially inside the network, and everybody is getting translated to the same outside address or global address. How do we maintain uniqueness to be able to identify how the untranslations take place if we're sending return traffic back? Well, we maintain a NAT translation table. And in that NAT translation table, we have things like protocol, source IP or inside local address, inside global address, the ephemeral port that the host is using to communicate, the outside local address, the outside global address, the well-known port that the client is using to communicate to, and so on. So by maintaining information about every one of those individual components of the data flow, we can uniquely identify those translations in the database, and then we can untranslate as traffic returns back. There is a limitation to port address translation because there's only so many ports that you have. Remember, we're talking about TCP or UDP port numbers in this case, and that's a 16-bit field in the TCP and UDP header, which means that we're limited to 65,536 ports, assuming 0 was useful, which it's not. All right, so that might seem like a lot of ports, but in reality it's not, because multiple clients or a client can generate multiple streams of information very easily. All right, now dynamic NAT, the one I skipped over, is what we call many-to-many. When you hear the word dynamic, you should automatically think pool, P-O-O-L, a pool of addresses. So what I would do in the case of a dynamic NAT profile is I would set up a pool of addresses, and then I would translate to that pool of addresses. The idea is that when the client needs to go out to the internet, it grabs an address from the pool. When the client is done going to the internet, it releases the address back into the pool so somebody else can use it later on. This might have worked in the 80s and 90s when we didn't go to the internet that much, but the reality is it's just not very practical for what we're seeing today. I mean, every client pretty much goes to the internet all the time, right? It's very common. So we do have a use case scenario for dynamic NAT. It would be used in combination with PAT, and I'll explain what that means a little bit later on. Okay? So what is static NAT? Like I said, it's a one-to-one translation. We have a policy defined on our perimeter device that says, if the inside local address is X, we're going to translate it to Y. And that happens every time. But the interesting thing about this type of NAT scenario is that that NAT information is stored in the translation table statically. All right? So it's kind of permanent in that regard. So that means a client from the internet can initiate a connection to an internal client, and that data flow will work just fine, or vice versa. The client from the inside can communicate outside, and so on. All right, there's basically three things to configure NAT. Two things in the case of static NAT. You identify which interfaces are participating in NAT, and then you set up your policy. Now, with a pool, with dynamic NAT, you have to set up a pool, and with the other types of NAT besides static, you have to specify or classify the individuals that are going to get natted. We typically do that with a access list, right, to identify who's going to get natted. All right, so this one-to-one translation, you get the idea. I don't have to go through each of the bullet points here, but basically we have a permanent entry in our NAT translation table that says this public IP gets translated to this private IP, and regardless of the flow of information, that NAT takes place. All right, so it's the responsibility of that perimeter device to essentially ensure that the profile is set up correctly and that we can actually do the translation. Now, dynamic NAT, like I said, is where we set up a pool of addresses. And again, not very practical if we're just using dynamic NAT by itself. Because the reality is, if you have 1,000 clients inside your enterprise, it's highly likely that you're going to need 1,000 addresses in your pool to support that. Does that make sense? So we don't really have kind of any limitation in that. There's a serious limitation in that regard because the pool has to be as large as the number of clients that you want to facilitate, which is really not very practical. But there is definitely a use case scenario for dynamic NAT. And we will see that in a little bit. But this is just an example of, hey, host 101 wants to go out. It's going to get translated to 201.5, so that's an address from the pool. The next client wants to go out. It's going to get translated to 201.6, and we're just simply grabbing addresses from the pool. And then once we're done, we release those addresses back into the pool. Port address translation is the most common form of NAT. It's what you run at your house. It's what you run in hotels, in businesses, where basically you have some sort of public presence on the internet with the connection to your service provider, typically on the outside interface of your perimeter device, and you're simply translating everybody to that address. Now, the name implies that we're actually translating ports. Port address translation, or what some people will call this version of NAT simply overload. Translating of ports doesn't actually happen unless it has to. So if you look at the table here, we can see that the first session, if you will, host 10.1.100, used an ephemeral port of 1723. That's the random source port. Got translated to the IP address on the outside of our router, 209.165.201.5, and the port was not translated. All right, no problem. The destination is telnet to 209.165.202.131. Then the next client establishes a session, 10.1.1.101, port 1927 as the ephemeral port, and again, the port did not get translated. As long as the ports are unique within the database, the ports don't get translated. Does that make sense? So far, the two sessions or the two flows that have been established, the ports are unique, so there's no translation taking place. But if you look at the third flow, 10.1.1.101:1723, that is a different client than 100, but it is entirely possible that that client could choose the same random source port that the other client chose. So in order for me to uniquely identify this flow, what the router does is it translates that port to the next available port. There's some algorithm that allows it to decide what port to use. And that means that every single entry in this database is unique, 100% unique. But there's a downside to this port address translation piece. It makes every entry unique, which is beneficial, but it also raises a problem. We no longer have 65,000 ports that we can deal with. We actually end up reducing the amount of connectivity that we have to about 5,000 sessions, not 65,000 sessions. And in a lot of organizations, you could reach that 5,000 limit pretty quickly. You could reach that pretty quickly. So how do we resolve that problem? Well, remember I said that there was a use case scenario for dynamic NAT? Remember, dynamic NAT is a pool of addresses. In most port address translation implementations, you are overloading the outside address of the device. So you're taking this single IP address and you're overloading that IP address multiple times. But you can also overload a pool. I could create a pool of addresses, set up in essence a dynamic NAT scenario, but by adding one single keyword, overload, to the end of my policy. So I would say IP NAT source static 1, pool, NAT pool, overload, right? The only difference between overloading a pool and not overloading the pool is having the overload keyword. So now if I have 20 addresses in my pool and I'm overloading the pool, I get, 5,000 times 20, 100,000 different connections. So that's kind of the use case scenario these days for dynamic NAT, is if I need additional addresses. Okay? And it goes through and it talks about this whole connection tracking concept and how we don't translate the ports unless we absolutely have to. It talks about the limit of the number of ports that we have based on a 16-bit field. So theoretically, that's 65,536 ports, and so on. But it's much less than that in most cases because of the port address translation need based on the pseudo-random ephemeral ports that the clients are using to communicate. All right. I'm not going to read all this because I basically described all this already. So which type of device would typically use the static NAT method of translation? Somebody's laptop, a stationary desktop, an accounting server, or a DNS server. I would say a DNS server. I mean, it could theoretically be an accounting server if that server's on the DMZ and it's housing public information. But DNS is more of a services-based type of server, so I would guess that they're looking for that as an answer in this case. All right. Now, in the past, when you set up NAT, there was a very specific configuration process that you had to go through. And that involved specifying which interfaces are on the inside of the network, which interfaces are on the outside of the network, and then setting up your policy, which you still have to do, by the way, but setting up your policy to say this is how NAT is going to take place. All right. As of iOS 12.3.14t, Cisco created something called a NAT Virtual Interface, or an NVI, which basically eliminated one element, and that is having to specify the inside and the outside address. You still have to have your policy. You still have to identify who's going to get NATed. The other most important piece of this is that the order of operations of the NAT process is completely different. All right, so here's an example of an NVI configuration. The access list is here just to simply classify who gets NATed. All right, so we're saying access list 10, anybody that has an address of 192.168.10.0 with a mask of 0.0.0.255 is going to get NATed. So we're matching the first 3 octets. Then we're doing overload, right? Ip Nat source list 10, that's my policy, global policy. And it's saying if the traffic is permitted by access list 10, it's going to get NATed to the IP address on Ethernet 01, and we're going to overload that address. So this is a traditional port address translation configuration. Now, normally what I would do is I would go into interface Ethernet 00 and I would say IP NAT inside, and I would go to Ethernet 01 and I would say IP NAT outside. That's what the classic configuration looks like. NVI removes that requirement to configure the inside and outside, and the order of operations, like I said, is going to be different as well. All right. With Classic NAT, with regard to the order of operations, Classic NAT first performs routing, and then it does the translating when it's going from an inside interface to an outside, and vice versa when the traffic flows internally. If it's coming from the outside, it's going to get routed and then untranslated. NVI performs routing, translation, and then routing again. So that means to say that we do that routing operation more than one time, before and after the translation. That gives you a little bit more flexibility on how you route the traffic. If you want to implement some sort of policy-based routing policy, you have that capability now because you're routing twice. You're routing before the translation and you're routing after the translation. So you might decide to configure a policy on your router that based on this inside local address, I'm going to choose to route the traffic this way, or based on the inside global address, I'm going to choose to route the traffic this way. Does that make sense? So it is a kind of a newer way of looking at the translation. All right, everybody, welcome back. We are now moving into discovery number 14, implementing NAT. In this discovery, the internal network, basically the network on the left here, consists of 3 different subnets, and we're using private addressing in this particular case. Each subnet is going to be used to demonstrate different types of configurations of NAT, which will include things like static NAT, dynamic NAT, and then finally the most common form of NAT, which is port address translation, so that we can access that internet resource. All the devices in the topology are kind of already prepared with their basic host name and IP address configurations. We have routing to the internet through the use of an already configured default route. The server and the servers in the network, the PCs in the network, they are just going to be Cisco routers that we're using to, use iOS commands to verify the topology. So we're going to configure static NAT on router 1 so that the internal server 1, can be accessed from the public internet. We're also going to configure dynamic NAT on router 1 so that those internal hosts, specifically in this case PC1 and PC2, can access the internet by being translated into one of the many possible public IP addresses that we have. We're also going to configure PAT on R1 so that PC3 and PC4 can access the internet by sharing a single public IP address. So just to give you guys an example of the different types of NAT that we can have in our environment. So the first task is going to be configuring static NAT. And we're going to be doing this essentially on our perimeter router. That would be router 1 in this case, which is the router between our private space, which we call our inside local space, and our public domain, the internet. Okay? Configuring static NAT is actually a really simple process. you have to define the inside and outside interfaces. We're not using the NAT Virtual Interface, so in this case we're going to use kind of a traditional configuration. Identify which interfaces are inside and outside, specify which inside addresses are going to be translated, and then create our policy, which is to say we're going to NAT our source information based on static, and then we'll specify our inside and outside addresses. We're going to do this in global configuration mode. So to configure static NAT translation between the inside local address and an inside global address in global configuration mode, we would type the command Ip Nat inside source static, specify the local IP, and then specify the global IP. All right. In addition, we would have to enable NAT on the interfaces. So we would go into our Ethernet 1.0 interface and say perhaps Ip Nat inside, and we would go to our Ethernet 1.3 interface and say Ip Nat outside. Now in this particular task, server 1 has an address of 10.10.2.20 with a 24-bit mask. It's going to represent a public server in a DMZ. We're going to use static NAT as a means for server 1 to be accessed from the internet. That's the idea anyway, all right? So even though we don't have a firewall, we don't have really the separate network designations, we're just trying to demonstrate the configuration concepts and the configuration elements. All right, now router 1 does have access to the public IP address space, but the systems within the private address space in this topology do not. So we need to verify this fact. One at a time, we're going to access the consoles of router 1 and server 1 and basically try to ping server 2, which has an address of 203.0.113.30. The pings should be successful from router 1, but they should not work from server 1. So let's go ahead and go into router 1 first. And let's go ahead and try our ping from router 1. All right, I didn't load up all the routers in advance in this particular case because we have or the devices, we have so many of them. But let's go ahead and ping 203.0.113.30. And that ping should go through. Doesn't appear to be working. All right, sorry about that. We had a missing configuration, so I went ahead and fixed that problem. Let's go ahead and try our ping again, 203.0.113.30, and I should be able to reach that destination from this router. Come on. Maybe my devices, I just rebooted everything, so maybe my devices haven't quite booted up yet. But let's pause the video and make sure all the devices boot up, and then we'll get started back up. All right, try this one more time, 203.0.113.30, and the ping does go through this time. Had to wait for some of the devices to boot up, and it just took a little while. So now let's go to server 1, and let's go ahead and do our ping from server 1, which in this case we know it should fail from server 1 because of NAT, right? There's no routing to this private address of this server. So if I do a show IP interface brief, we can see that server 1 is 10.10.2.20. If I ping 203.0.113.30, it's not going to work because we're sending the packet from 10.10.2.20, and we are getting a destination unreachable because the router doesn't know how to route back to that destination. All right, which makes sense because NAT hasn't been configured yet. The internet router, which in this case is R2, is getting the packets from the private IP address of 10.10.2.20, and it's basically dropping those packets. Routers on the internet, as you're probably aware, don't know how to route to private address space, what we call RFC 18 address space. So our first task is going to be to configure router 1 interfaces with static NAT. Ethernet 1.1 is on the inside, and Ethernet 1.3 is on the outside. Let me just pull up the diagram and show you. This is the one we're configuring for the server. This is kind of our DMZ subnet, if you will. And this is the public-facing internet interface, which already has a public IP address. So the first, in classic CLI NAT configuration, the first thing you want to do is you want to set your IP NAT inside and IP NAT outside interfaces. All right. Now, I want to be clear about this. Just because you turn NAT on a particular interface doesn't mean now that a policy has to match. If a packet arrives at the interface and the policy doesn't match, or there is no NAT policy defined, then the packets will simply get routed as they normally are. We don't necessarily have to NAT. We're just saying that these interfaces are participating in NAT. All right, so we've enabled NAT essentially on the interfaces. Our next step then would be to go ahead and define our translation rule. Now in our case, we want to go ahead and we've got a group of public addresses that are routed to the outside interface of the router, our internet-facing router. So we're going to go ahead and add a static NAT configuration entry that's going to translate the server 1 IP address of 10.10.2.20 to 198.51.100.20, and then we're going to test again. All right, so let's do IP NAT inside. So we're going to NAT based on traffic coming from an inside interface. The source of the NAT is going to be a static NAT. The inside local address is going to be 10.10.2.20, and the inside global address, which is basically how we're going to represent ourselves to the rest of the world, is going to be 198.51.100.20. Now, the interesting thing about static NAT configurations is that they are permanent in the NAT table. In other words, well, by definition, they're static, so they're permanent in the NAT table. And this also means, by the way, that they are bidirectional because we already have an entry in the database. Traffic can originate from the outside or traffic can originate from the inside, and the translation should take place. So I'm going to access the console of server 2 and establish a telnet session to server 1's inside global address, which is the one that we set up as 198.51.100.20. Basically, it's kind of like simulating an internet user accessing the server in a DMZ, and the username is admin, and the password that we set up is Cisco123. So let me go to my topology diagram, and this will be my client on the internet, and I'm just going to do a basic telnet and see if I can't authenticate to that client. So we're going to go to the inside global address of 198.51.100.20, and we're going to put in a username of admin and a password of Cisco123. And as you can see, we are now connected to that device. Now, if I go back to my perimeter device and I do a show IP NAT translation, we can actually see the active session for the NAT profile. All right. Now, this is the protocol, which is TCP because it's telnet. Inside global is the translated IP. This is the destination port number for telnet. Inside local is the real IP. This is the destination port number for telnet. Outside local and outside global are almost always going to be referenced as the same address. And that's because generally we don't know what the real IP address is of a client on the internet. So oftentimes we won't see any other designation here. Now the 47307 is really just that ephemeral port that router used or server 2 used to be able to establish the session, that TCP session. So let me go ahead and get out of this telnet session here. And as you can see, that was a really, really simple configuration. Just a quick review. Show, run, pipe, section, NAT. It was basically just 4 commands, right? We wanted or 3 commands, excuse me, identify the interfaces that are participating in NAT, and then set up your NAT policy. Probably one of the easiest forms of NAT to create. And if I had additional static entries that I had to create, I would just simply go ahead and add more rules. And as long as the packet matches the rule, the packet would get translated per the rule. If a packet came to the interface and didn't match the rule, then the packet would just be routed normally. Okay? So in our second task, we're going to go ahead and configure dynamic NAT. Now, whenever you see the word dynamic, you should always think of one thing: pool, a pool of addresses. Dynamic NAT is probably one of the least commonly used forms of NAT, at least by itself. We can overload a dynamic NAT policy, which is pretty common in large enterprise environments. But dynamic NAT as itself without overload is pretty much not very useful, right? Because back in the day, you didn't have that many clients going out to the internet. You didn't have to have a whole lot of public IP addresses. But nowadays, pretty much everything does. So you would essentially have to have a large enough pool to assist in all of the clients being able to communicate. Well, that kind of defeats the whole purpose of NAT in the first place. So dynamic NAT does differ also in the configuration from static NAT, but there are some similarities. Just like static NAT, we have to configure the interfaces that are participating in NAT, inside and outside, and so on. But rather than creating a static mapping to a single IP address, we have a pool of inside global addresses that we're going to use, and then we're going to create an access control list for classification, not for security purposes, but for classification to identify which clients are going to be translated. So we have this kind of ACL to NAT mapping, and that's going to be defined by our policy, our Ip Nat inside source policy. So the first step would be to go through and possibly create the pool. And then the next step would be to set up maybe your access list to identify who's going to get translated. We could use the overload keyword. I'm going to talk about what that represents as I go through the configuration. And then we have to do our NAT inside and our NAT outside. Now remember, in our particular topology here, PC1 and PC2 are addressed in that same private space. Well, different private space, but the same general RFC 1918 address space. Specifically for these two clients, it's the 10.10.1.0 subnet. And we're going to use dynamic NAT as a means to allow these clients to communicate to the internet. Now, R1 does have access to that public address space. Again, the private devices do not. And if I go into PC1, for example, let me go back to my topology here, and I try to access that public server, it's going to fail. Just with a basic ping, we can test that theory. So if I do a ping to 203.0.113.30, that ping is going to fail. All right. In fact, it's we get an unreachable. It doesn't time out, but we get an unreachable indicating that, hey, the packet went out, but then it didn't know how to come back. Okay. So let's start by defining a pool of global addresses. So we're going to go back to our perimeter router, and we're going to say config t Ip Nat pool, and we're going to give the pool a name. Now, I generally like to make sure that my names are in all caps, so that for anything that I name in my system, whether it's an access list or a route map, or it could be, some policy-based routing policy or QoS policy, whatever it might be, I want to make sure that I am naming those in uppercase, because then when I'm parsing the configuration, I'm analyzing the configuration, it's going to be very, very easy for me to identify the difference between maybe command syntax and the name of something. All right? It certainly doesn't make a difference with regard to the function or the operation. All right, so let's go ahead and say our pool starts at 198, 51, 100, 100. So we're going to start at 100, and we're going to say 198, 51, 100.149, and we're going to say a net mask. Now, the net mask piece is interesting, right? Because with the net mask, we certainly don't carry net mask information within the packet header. That's not very typical. Actually, it's not done at all, right? There is no field within the packet header for net mask. But we are specifying the net mask for the pool because we want the router to be able to identify if any of the particular addresses that are included in the range could not be assigned because maybe they're a network ID or maybe they're a broadcast ID. So by specifying the net mask keyword, I'm able to identify to the router, hey, if I happen to include a network IP, a network ID, or if I happen to include a broadcast ID, go ahead and remove that from the pool, if you will. Don't assign those addresses. All right. The next step is going to be creating an access list. Now, there's a couple of ways that you can do this. You could do a standard a named access list. I'm going to do an IP access dash list standard. Remember, we're doing this based on source address. Standard, and then I'm going to say NAT, NAT1. All right. And then I'm just going to say, let's go ahead and permit the 10.10.1.0 subnet, the whole /24 subnet. Now, again, you don't have to use a named access list here. In fact, numbered access lists pretty much become named access lists as far as management and all that goes. But I like to keep it clean. I like to know what my access lists are for. I could say NatLan 1 or whatever, something that would indicate, something about that particular purpose, right? The purpose of that. All right. So that being said, the next step is to go into our interface. And in this particular case, we're talking about PC1 and PC2. So that's going to be this Ethernet 1.0 interface. And we're going to say IP NAT inside. All right. We don't actually have to apply the IP NAT outside because we already did that in our previous task, right? So if we do a show IP NAT Statistics, we should be able to see that NAT configuration. Yep, there's my outside interface. Here are my inside interfaces. I have one static translation. I don't have any active dynamic translations because we haven't generated any traffic yet. I have an expired translation. That was that static configuration that I did before. All right. So the last step, we don't see the dynamic rule here because we haven't actually created our policy. So I'm going to say IP NAT inside source list NAT1 pool, and what did I call it? NAT pool. Now, let me talk about the option for overload because we do have the option to do overload here. If I choose not to use the overload option, this is the total number of addresses that we can translate to. Basically 150 or 50 addresses, I should say. If I were to use the overload keyword, we would actually use essentially port address translation for each of these 50 addresses. And that's really the most common use of dynamic NAT today, is to overload a pool with the overload keyword so that we can in fact generate lots and lots of traffic. We're not going to do that in this case because we only have 2 clients that we're concerned about, but now I should be able to go back to my PC now and do my ping. And sure enough, I could do the ping. All right, now if I go back to router 1 and I do a show, let's do a statistics first, since we looked at that before, and we can see now that we have some dynamic entries. We can actually see the pool information as well, right? Here's the policy, here's the pool, 50 total addresses. We've allocated one of those addresses, which is 2% of the pool. And if I do a show IP NAT, translations, we will see that translation in the list here. So here's our protocol, ICMP. This is the inside global, inside local, and outside global. This 1 is here to represent the connection number, right? So if I go to PC2, for example, and I do basically the same thing, because we're not using ports in this particular case, we're using essentially a layer 3 protocol with no transport layer function. We are going to differentiate between these connections based on that number, which is not technically a port number in this case. It's basically, I'm sure there's a technical term that describes it. Well, the other one timed out. Let me go ahead and do the ping here again so we can see the multiple entries. So we can see here that each of these are going to increment with a unique ID, if you will. It's just a way for us to uniquely identify the client. And we can see this is 100, 101. So obviously there's other ways that we can identify these clients individually, but that's the purpose of that particular number. All right. So if I was to do this quickly, the extended translation that gets associated with the ICMP session is going to have that individual number, right? We could resend a ping and so on, but the ICMP sessions are very short-lived, but TCP translations, they have a 24-hour inactivity timeout period. There's just basically a simple entry in the table, and we see that here. So we did our ping from PC1, we did our ping from PC2, and we can see the entries in the database here. Now the extended ICMP entries that get associated with the ping activity, like I said, because it is ICMP, they're going to be short-lived, and I had to kind of actually generate that traffic a couple of times. Now if I go back and I look at my show Ip Nat Statistics, I can see that I've allocated 2 addresses from the pool. Now I'm up to 4%. I can see how many packets were translated, how many dynamic entries I have, and so on. So we can kind of monitor the pool. We were, translated up to 2 clients in this particular case. All right. So let's clear the translations. Let's do a clear Ip Nat translations, and let's do all of them. All right. So if I do a show Ip Nat translations, I should see that all those translations are now gone. All right. Of course, the static entry will always remain. That doesn't change. All right. The static entry will always be there. That's the whole point. So the last task that we have in this discovery is to go ahead and configure what I would consider to be the most common form of NAT, which is port address translation. All right. Now to configure PAT, we still do the same thing that we did with static NAT and the same thing that we did with dynamic NAT, right? And that is to say Ip Nat inside and Ip Nat outside on the interfaces. We're still going to define an access list, right? That access list is going to allow us to classify who gets natted. Whoever's permitted by the access list will get natted. Whoever's not permitted by the access list will not get natted. And then we have to specify our PAT policy, which is to say Ip Nat inside source list, and then reference the access list, the interface, and then, of course, the most important piece is overload, and I'll talk about that again. So in our particular example here, PC3 and PC4 are the PCs. They're on Ethernet 1.2, and they have their own respective addresses. They're actually in the 3 subnet in this particular case. So the first step is, we could certainly come into PC3 and do a ping real quick and see if we can ping. We know it's not going to work, but let's go ahead and verify that. Let's do a ping to 203.0.113.30, and the ping fails because, again, NAT hasn't been configured. So my next step is to go ahead and configure an access list on router 1. And this is subnet 3 in essence. So I'm going to do IP access dash list standard NAT 3. And I'm going to say permit 10.10.3.0 0.0.0.255. Okay. I also need to go into interface Ethernet 1.2. I have to do an IP NAT inside to enable NAT on that interface. And then verify, do show IP NAT Statistics. We can see now that we have 3 interfaces that are participating on the inside. And we can also see that we still have pretty much the same information here. Because PAT, we haven't defined the policy yet, so we don't see the PAT policy listed here. And that would be really kind of the next step, wouldn't it? Let's go ahead and define our policy. So we're going to say IP NAT inside source list NAT 3. And then we're going to say, let's go ahead and translate this traffic to the IP address on interface Ethernet 1.3. Now, if I was to hit return here, only one connection would be allowed because I would only be able to use that interface one time. So oftentimes this type of NAT is referred to as overload because basically we're saying let's go ahead and use this interface over and over and over again. Here's the downside to that though. There's only so many port numbers that we're going to have. All right. In that range of, I mean, we have 65,000 something port numbers, but the key is that obviously some of those are well-known ports and many clients are going to be generating their own port numbers and so on. I mean, there are multiple port numbers and so on. But in any event, we're overloading that interface. Now, if it turns out that we don't have enough port numbers for overload, then the next thing that would have to happen is we would have to go to dynamic NAT with overload where we would have a pool of addresses and then based on that pool of addresses we would be able to overload the pool and we could extend essentially the life of our overload configuration. All right, so we've done our policy. Again, let's do a show IP NAT Statistics and now we can see we have NAT ID 2, which is our overload to the interface of Ethernet 1.3. So let's go ahead and go into PC3, and we're going to do our telnet to 203.0.113.30, and we're going to put a username of admin, Cisco123, and now we have an active session. So if I do show IP NAT Translations, I can see that TCP session is active on that device. Now, if I go to PC4 and I do the same thing with PC4, I want to point out a couple of things here because this is one of those common misconceptions. Telnet 203, 0.113.30. All right, admin, Cisco123. Again, go back to router 1, show IP NAT Translations. Now let's take a look at this database here. Because you can see here actually that we are doing some port address translations. And that's where the term port address translation comes from. This is the outside destination, port number is 23, it makes sense. This is the inside host, and these are the inside local addresses. These are the ephemeral ports that are being used, but notice the router is translating those ports and assigning ports sequentially for those destinations. That's where the term port address translation comes into play. Now actually this really should not be happening in this particular case because, and I was hoping it wouldn't show that, but it does in this particular case. Probably a viral thing, IOSV thing, but the only time, and this is what I was going to point out, the only time that port address translation should really take place is if two different clients happen to use the same ephemeral port. So if this was 62.419 and this was 62.419, that's when you would see the translation occur here. So what we should be seeing is 62.419 here, and 62.419 here, 23563 here, and 23563 here. All right. Otherwise, we would run out of ports very, very quickly in that case. I'm not sure why IOSV is doing this in this particular case, but I just wanted to make a note of that. So if you happen to have real iOS devices and you want to test this out, just go ahead and test it out. All right, and you'll see what I'm talking about. Do show Ip Nat Statistics. Again, we're seeing now, of course, our dynamic NAT is not being used right now. This particular NAT, we don't really see kind of any indication that the NAT is happening. We do see it here, extended NAT, but we don't actually see the active translations. So it gives us some information, but not a whole lot, right? Obviously, the statistics that are being displayed in our lab environment, are not going to have as much information as what you would see in a production environment. So let's go ahead and close out of PC3 and PC4. And as I terminate these sessions, and I go back to router 1, do show Ip Nat Translations, I should eventually see those time out. It might take a while, actually. Remember I said that the lifetime is about 24 hours. I could certainly clear those translations. Do clear Ip Nat Translation star. And you can see that they've gotten cleared out. All right. So which dynamic option enables one public address to be used for multiple private hosts? That would be port address translation, right? One public IP, which is typically going to be the IP address on the external interface, which already has a public IP. That's going to allow us to translate those private hosts. All right. And again, if we have a web server with a private IP address in our network and we want users to be able to access it from the internet, that's where Static Nat is going to come into play. So pretty basic configuration. There is one other thing that you could do, for example, so that you could see NAT happening in real time. Be very careful with this, debug Ip Nat Translations, because obviously if this is a pretty large environment, you're going to potentially overload the device with these debugs. But we can definitely see the translations taking place, right? Here is the source port. Here's the destination port. Excuse me. This port is being translated to 4096. Source IP being translated to this IP, destination IP, and so on. So we can see the traffic flowing back and forth. We can actually see the packets being translated and routed. All right. So that's one thing that you could do. There's some other kind of verification and debugs you can do with IP routing and so on. Just have to be very careful with these particular debugs because they can obviously, you can saw we just did a telnet session with 2 clients and this is the amount of traffic that was generated. So it can overwhelm your console pretty quickly if you're trapping this information to the console. All right, so we're going to go ahead and wrap up this lesson and we will see you guys in the next discussion. And we're going to jump into some more discoveries down the line, so we'll see you there. So let's go ahead and go through the rest of the summary challenge here. We'll wrap up this section. Which option enables one public IP address to be used for multiple internal private hosts? Well, that's a repeat, right? Pat, web server with a, yeah, this is a new one. You have a web server with a private IP address within your network. Oh, that's also a duplicate. Okay, great. Here's a new one. You enter the show Ip Nat Translations command and do not see any translations. You're worried there's a problem. What would be the most appropriate action to test the NAT operation? Issue a ping from the device inside the network that should be translated. Verify the running config or to find a configuration error. Issue the ping command from the router to any address outside the network. Issue a trace route from the router to any address on the outside of the network. The last 2 are out. And the reason the last 2 are out is because traffic that's originated by the router itself doesn't have policies applied to it. Just like access list policies don't get applied to traffic originated by the router itself, neither do NAT policies. So we would want to ping from the device that should be NATed. The only reason we might not see translations is because we didn't have any active flows. So we have to generate traffic to generate a traffic flow. You issue the command clear IP NAT translation star. However, the translation table still displays entries. Which two reasons possibly could cause this? Well, the translations are still used by hosts. That's true, right? You can clear the translations and they can just reinitiate and get repopulated if you have active flows still happening. Port address translation entries do not remain in the table. Static entries remain in the table. So those would be the two reasons. What is the difference between NAT and dynamic NAT? Static NAT and dynamic NAT. Well, static NAT is a one-to-one. Dynamic NAT is a one-to-many. Nope. Static NAT maps one-to-many. Static NAT is one-to-one. Dynamic is many-to-many. Yep. That would be the right one. Static NAT is always one-to-one. Dynamic NAT is lots and lots to maybe a little bit less, right? Because the pool is usually going to be smaller than the number of clients that you have inside your enterprise. Which of the following translation technologies would typically be used at home, especially for connecting devices like tablets, phones, and PCs through your cable internet connection? That would be port address translation. It has nothing to do with the fact that you have tablets, phones, and PCs. They're just saying you just got a bunch of junk that's connecting to the internet. We're going to typically use port address translation. By the way, NAT does exist in IPv6. All right, I didn't mention this. I should have mentioned this as part of our discussion. But it has somewhat been deprecated. Every address in IPv6 is usually public. We're still going to have all the security features in place to protect our network, so we're not vulnerable to attack. But we can get away from NAT with IPv6 because of the vast amount of address space, and IP can operate natively like it normally does. But NAT does exist in IPv6. The concept of private addressing exists in IPv6 as well. FC00:/7, I think it is. FC00:7. Yeah, I think that's the site local address space. But which command will display the router interfaces that are configured as NAT inside? Show Ip Nat Statistics. Remember, that's the it shows us a bunch of other stuff. Which option enables one public address to be used for multiple internal private hosts? This is a repeat, but that's Pat. Okay, so we're done with that section. We'll see you guys in the next section.